Robots. The key component of modern industry, the so-called Industry 4.0. They're at Tesla, Porsche, Coca-Cola, Airbus, Boeing, Bentley, Siemens, Pirelli, Mercedes. Well, just to name a few. Robots are truly incredible machines, capable of performing various tasks with high speed and precision, without the need for human intervention. And there are currently several robots, each designed and built to perform a specific task. But why are they dominating industries? And why are more and more companies choosing robots as their main workforce instead of humans? Aren't they taking away that dream job? First, we need to define what an industrial robot is. According to ISO, the International Organization for Standardization, an industrial robot is a multi-purpose manipulator, automatically controlled, reprogrammable, and programmable in 3 or more axes. Or, a robot is a mechanical system of varied geometry, made up of rigid bodies articulated with each other, designed to support and position or orient. The end effector, which equipped with a mechanical gripper or specialized tool, is in direct contact with the process. Well, leaving aside these simpler definitions, we can say that a robot is a programmable mechanical device used in place of people to perform precise or repetitive tasks with a high degree of accuracy. And there are currently about 22 companies that manufacture these robots, with ABB and KUKA being some of the main and most renowned companies in the field. They manufacture these robots, with ABB and KUKA being some of the main and most renowned companies in the field. The first company to produce industrial robots was Unimation, founded in 1956, and the first industrial robot was named Unimate, created by George DeVol and installed in a Ford Motor Company factory in 1961. When it comes to how humans and robots perform tasks, we can take the following aspects into consideration. For a skilled human, at the beginning of performing a given task, the graph would look something like this, with precision, concentration, speed, accuracy rate, and repeatability capacity being quite high, while error and fatigue are quite low. Currently, the human is performing the task at their best, with great agility, flexibility, and minimal error. If we give the same task to a robot at the beginning of performing the task, the graph would look something like this, with the robot performing the task with high precision, accuracy rate, speed, and repeatability, while the error would be at much lower levels, and fatigue would not exist. After a few hours performing the task, the graph for the human would change drastically and would look something like this, with precision, concentration, speed, and accuracy rate greatly reduced, while error and fatigue, which previously hardly existed, are now at much higher levels, causing the quality of the final product to be compromised. That's because humans need regular breaks so that precision, pace, and concentration can be restored. For the robot, after a few hours performing the same task, its graph would remain the same, maintaining the same high levels of precision, accuracy rate, speed, and repeatability, as well as the error, which would stay at the same low level. That's because robots don't get tired even after several hours of continuous work. The only real difference is the robot would be a bit warmer, but this wouldn't impact its performance. This demonstrates the potential that robots have in performing tasks continuously and repetitively for long periods of time. And it also explains why several companies choose robots as their main workforce on assembly lines where precision and repeatability are key and critical factors, in addition to other factors that we will see later on. Robots can be divided into 6 categories or types: Cartesian, articulated, cylindrical, SCARA, Delta, and Polar. In this video, I will focus on articulated robots. An articulated robot, also known as a robotic arm, is the type of robot most commonly found in industries. They have joints and movements that resemble those of a human arm. Their typical applications include painting, casting, welding, material handling, product inspection, and quality testing, all performed fully autonomously, with high precision, speed, and repeatability. Robotic arms, commonly used by companies like Tesla and Porsche, are robots that have 6 axes of movement, known as degrees of freedom, or movement axes, which refer to the robot's freedom of movement, that a rigid body, in this case the robot, has when moving in 3-dimensional space. These axes can be divided into 2 classes: the axes of the robot's base and the axes at the end of the robot. The axes of the robot's base are a set of 3 axes that allow the robot to move to a specific position in space. These axes are called waist, shoulder, and elbow. The waist is the first axis of the robot and allows the robot to rotate 180 or 360 degrees in relation to its base, which can be fixed like these robots or mobile like these. This rotation is done by an internal actuator. The shoulder is the second axis of the robot, which allows the robot to move forward and backward. The elbow is the third axis of the robot, which allows it to move up or down. The other 3 axes belong to the class of axes at the end of the robot, with the first one, which corresponds to the robot's 4th axis, being responsible for rolling movements, and the 5th axis being responsible for up and down movements. And the 6th axis, also called the end effector, is responsible for rolling or gripping movements, as in the case of robots with pincers, or in other cases, it can be fixed. The configuration of these last 3 axes can vary depending on the application and the task for which the robot was designed. So, if the robot performs welding, the 6th axis will be for gripping. If the robot performs painting, the axis can be either rotary or fixed depending on the robot. The latest generation robots found in major automotive industries have a wide variety of systems that allow the robot to move to many different positions. For the robot to perform its tasks, it needs actuators, gearboxes, cameras, sensors, servo motors, as well as complex programming. The use of sensors allows the robot to obtain information about itself and its environment in order to perform the work it was designed for, as well as to modify it according to that information. Sensors can be grouped into 2 main categories. Internal sensors, which provide information about the robot's own variables. These sensors can be optical encoders, also known as encoders. They are on the robot's axis and tell its computers how far the motor shaft has moved from its initial position. This is possible thanks to light-emitting diodes, or LEDs, which emit light, and based on how much the motor has moved, this light is obscured. This allows precise measurement of the motor's movement and the robot's position. There are also other encoders found inside robots, such as synchros, resolvers, multi-turn potentiometers, tachometers, among others, which work together in the robot's operation. The other type of sensors are external sensors, whose purpose is to obtain information about the environment around the robot. Usually these are safety sensors for human protection, such as light curtains, ultrasonic sensors, mechanical barriers, pressure-sensitive devices, contact sensors, optical sensors for determining distances and obstacles, and object recognition, lasers for determining the proximity of parts to be handled, among others. Equipped with all these devices, robots are able to have a good sense of the environment around them, as well as precise information about themselves. The other key component in robotic arms are the actuators, which are devices that cause movement in the robot's axis. These can be linear or rotational movements, meaning they allow the robot to move up or down, as well as perform rolling movements. An actuator converts some type of energy into mechanical movement. The 3 most common types of energy used to power robot actuators are pneumatic, electric, and hydraulic. Hydraulic actuators have high torque and fast response speed, making them suitable for handling heavy loads. However, they require equipment such as pumps, which means frequent maintenance is needed, and they also generate a lot of noise. Pneumatic actuators are cheaper and simpler. However, they cannot be controlled precisely. Currently, direct current and alternating current electric motors are the most attractive for use in robotics due to their lower cost and because they are quiet. Thus, robots that have actuators powered by electricity combined with gearboxes allow precise movements in the different axes of the robot. But even so, they still wouldn't be able to perform any tasks because the most important part is missing: their software and programming. Programming is the most important, most complex, and most time-consuming part of the entire robot acquisition process. Programming determines what the robot will do, how it will do it, which tools it will use, and its start and end points. And all of this must be done with precision and within a set time frame so that the next stage of the production line can begin. Choosing the correct programming language is one of the major challenges and requires a lot of knowledge in the field, since each robot is designed, built, and programmed to perform a very specific task. Currently, there are more than 1,500 programming languages in the world, and to make things even more complicated, several robot manufacturing companies have their own programming language. For example, ABB has its own programming language called Rapid. KUKA has the KRL language, and Kawasaki uses the AS language. But the popular languages in the robotics industry boil down to C#, .NET, Java, Python, C, and C++. But there are other languages that are widely used for specific purposes, such as MATLAB, which is used by engineers for data analysis, research, data processing, and the development of control systems. There are also HDLs, hardware description languages, used in programming electronic devices and robots. The company KUKA offers the KUKA Architect family, which is a set of various software tools designed for programming robots to perform specific tasks. For example, KUKA Pallet Tech is software that allows programming and configuration so that the robot can perform palletizing functions with various packaging patterns. Meanwhile, KUKA Gripper and Spot Tech allow collaboration between multiple robots so they can perform gas-shielded welding and plasma cutting. There is also KUKA Vision Tech, which enables image processing thanks to effective tools for 2D object detection, quality control, code detection, among others. With this, the same robot can be used for different applications without the need to acquire new ones, making the robots more versatile and reducing costs for the company. That happens at Tesla with some robots. The same robot that installs the seats inside the car later changes tools and starts installing the front and rear windows in the same car, all completely autonomously. The price of the robot can vary a lot depending on the condition, whether it's new or used, the application, and the load capacity the robot can handle. For example, the KUKA robot, model KR200 and KR210, which can carry up to 200 and 210 kg. It's widely used in Audi, BMW, and Mercedes factories for seal-in applications, load handling, as well as in parts assembly, and costs $37,000. That's just for the robot and the controller. The KUKA robot, model KR500, which is used for assembly, cutting parts, inspecting parts, and handling heavier loads, has a price that ranges from $96,000 to $120,000. Some robots cost more than $400,000. But when some peripherals are added, such as controllers, SmartPad, specific software, and tools for handling loads, the cost rises to more than $800,000. In some cases, it exceeds $1 million,